We're going to continue our Bootcamp 4 with Excel and VBA by looking at the final example, another reactor example. This one has some distinctions from the ammonia reactor that we looked at previously. And it is an example taken from Scott Fogler's kinetics text, Elements of Chemical Reaction Engineering. And you can see the description here. It's a fairly simple reaction of cracking acetone to ketene with a byproduct of methane. There are, for this example, some operating conditions given in terms of a feed with various units. Also, specifications of the type of reactor used. This is a tubular reactor with many small tubes. The reason for that is that the reaction requires heat exchange to counter the endothermic nature of the reaction, which otherwise would just shut the reaction down by cooling it. The inlet temperature and pressure are given here because we're dealing with not with a packed reactor, but empty tubes. For our purposes, we'll assume that the pressure drop is negligible, and we're considering providing the energy in the space around the tubes, in the shell space, by using air with an inlet temperature somewhat higher than the inlet temperature of the acetone. All of this, obviously, is in vapor phase. So let's continue this and take a look at the reaction kinetics, which are fairly simple, first order reaction in terms of the consumption of acetone, and given a reaction rate here in terms of the time units of hours, a rate parameter, and our concentration in kmols per cubic meter. The temperature in terms of determining the rate parameter is provided in kelvins as usual. And then we'll start assembling additional information which we will require, getting expressions from standard sources for heat capacities as a function of temperature here. For acetone, a third order polynomial, ketene, fourth order, and for methane, third order polynomial plus an inverse term in temperature squared, where this is scaled temperature, temperature in kelvins divided by 1000. And then for each one of these, we can consider formulating based on a reference temperature and average heat capacity by integrating the above expressions. And then if we convert the temperature here over to the scaled temperature, we would then need to multiply that by 1000 in order to have the expressions come out correctly. Also, we note here the heat of reaction at 25 Celsius, and it is positive, indicating that it is endothermic. And then the heat of reaction at any temperature can be computed by taking the base heat of reaction and then multiplying by the changes in enthalpy of the individual chemical constituents, and that change can be computed by integrating the appropriate heat capacity from the reference temperature up to the operating temperature that has been scaled again by 1,000. So moving on with putting together the elements of our model, we need the concentration of acetone in order to complete the kinetic description. And we show it here, assuming pressures are moderate in terms of the ideal gas law, and applying for the feed of acetone with the feed temperature, we can come up with an initial concentration in kilomoles per cubic meter. Then carrying out material balances, we've got our disappearance of our flow of acetone with respect to volume given by the disappearance rate. And then this allows us to calculate the concentration of acetone for that expression, at any temperature based on our value that we have up here for the feed temperature. And then for the flows of ketene and methane, those can be achieved simply by applying reaction stoichiometry, and then the total flow by summing the flows of the three constituents. As far as the energy balance goes, we can make an enthalpy balance and account for the energy transfer from the air stream to the reaction stream inside the tubes, with an overall heat transfer coefficient and an area for heat transfer per length of tube. This allows us to find the enthalpy, and that enthalpy can, of course, also be described by the enthalpies of the three components. And then the enthalpy of each component can be described in terms of the temperature. And we'll see how that works into the calculation here in a minute. For the air, it has countercurrent flow, so we have to put in a minus sign here, and that this shows transfer from the reaction mixture to the air. And then when we apply the minus sign over here, it reverses that. So we end up with the air minus the temperature of the reaction mixture. And then, again, the enthalpy of the air can be described in terms of the temperature. And we note here by using standard conditions that the reference enthalpy of the air is 0. Okay, so we need to put all of that together, and we again use an information flow diagram where we tabulate our differential equations for the flow of A, the enthalpy of the reaction mixture, and the enthalpy of the air. And then solving these by numerical methods, we get the dependent variables, and we see how they figure into the rest of the model. So for the flow of the acetone, we can use that by stoichiometry to get the flows of the other two constituents, and then the total flow. Having that, we then come down here and we supply the molar flows to this relationship for the enthalpy of the reaction mixture, and this allows us to solve this nonlinear equation with the numerical method to determine the temperature. Once we have the temperature, that allows us with the total flow and the flow of the acetone to compute the current concentration of the acetone, and that completes the rate expression, which gives us what we need here. These two equations, this one gave us the enthalpy. We can, from this one, get the enthalpy of the air. Each of these, of course, we have to be given an initial condition. And then we can solve this iteratively as an algebraic expression to determine the temperature of the air, and that goes into these expressions. And then, of course, the temperature up here allows us to determine the rate parameter. So this is the reference that we would use for what we call the full model that allows the change of heat capacity with temperature. We have reasonably significant changes in temperature in this reactor. And this is the full model, and then we'll see now what we can do about making simplifying assumptions, come up with something not quite so complicated. And to do this, we work on the enthalpy balance, where we take the enthalpy and use the total enthalpy being the component enthalpy, and then use the product rule to come up with these two expressions. The first one of these corresponds to the expression here, corresponds to our rate expression, and then over here, this particular expression corresponds to heat capacity dTdV if we assume a constant heat capacity. If we put these together for the overall for a component, then we can sum these with the stoichiometric coefficients in order to get our change having to do with reaction. This then allows us to formulate from the above expressions a differential equation for temperature for the reaction mixture, where we need the heat of reaction, the heat transfer, and we're assuming here constant heat capacity, usually taken at some mid-range temperature. On the air side, it's somewhat simpler. We have our beginning energy balance. We assume constant heat capacity and a constant molar flow rate. And by doing that, we end up with a fairly simple relationship for the differential equation of temperature of the air versus volume. And this simplified model can then be formulated, and we don't have to solve any implicit algebraic equations to determine temperatures, because we now have differential equations for temperature, so we can solve those. And then having all of these, it simplifies how we're able to determine the rate parameter, concentration of A, and the differential equation for the flow of acetone. These stoichiometric relationships are the same as before. So we can consider the simplified model a little bit easier to handle, or we can consider the full model, all right? So we'll come back to this picture of the simplified model as we consider a spreadsheet solution and solution strategy for this. So we're going to consider how we do this, because we have a dilemma to address, and that is that we know the temperature of the air that is fed to the reactor, but that is fed at the end of the reactor where the reactants exit. So what we can do is we can estimate the final air temperature, which exits at the volume equals 0 point, and then we can solve our model forward to the full volume of the reactor, and that'll allow us to determine the air temperature from the solution. Now, we have a specification because the air temperature at volume equals VR is actually the feed air temperature. We have a specification for that. So we have to check the computed air temperature against the specification. If they're equal or close, we're finished. And if not, we have to come back around. We have to adjust the final exit air temperature and continue this until we get convergence. And this we do with the use of Excel's solver. And it's quite convenient for this. So what we're going to look at now is a spreadsheet which organizes this simplified model first. And we're obviously not going to construct this from scratch, but we'll present it to you and show you the results. And then we will move on and look at the full model. Okay, so let's go over to our spreadsheet here. And I need to open a file here. Which is PFR Simplified. Simplified model, all right? So this has very similar layout to what we dealt with the ammonia model. And that is we have a block of basic data and operating conditions up here. This specifies the reactor, the number of tubes, total volume inside the tubes, etc., and the tube length. And then we have area based on this, and heat transfer coefficient, which we acquired an estimate. We have our feed conditions, and then basic data on our components here for air, and have the acetone feed rate and the initial acetone concentration. We're going to take 200 steps in solving this, and then we're going to put in here more on the air feed, and we know that the feed temperature of the air is supposed to be 1250 kelvins, and so what we're going to do is estimate the exit air temperature, which occurs at volume equals 0, and we're going to see how that works out. So we'll check that in a minute. We've got the information on our reaction kinetics here, and then we have more information over here. Have heat capacities at 1000 kelvins, all right, and the heat capacity of air at 1100 kelvins, all right. Sorry about that. And then here, what we've done is we've taken a look at sensitivity of analysis based on our correlations of what about this approximation of constant heat capacity. So we're just testing this out by looking at the heat capacity and heat of reaction, all right, at different temperatures for our components, and then looking at the kind of changes that occur between 1000 and 1200 kelvins. And we can see that there is some change here. It's less than 10%, the change in the heat of reaction is actually less than that. It just gives us a little bit of an idea of what we're sacrificing by assuming constant heat capacity and heat of reaction. So we come over here and we've got headings. So let's move this to the top so we can see how this is arranged. We've got reactor volume, all right? And you can see this is in cubic meters. And if I go to the bottom, it goes down to 2 cubic meters, all right? And then I go across my, what we call the initialization row, and as you might see up here, this is a pointer to the feed. There is no ketene, no methane, and it should be up here. So our total flow is equal to the flow of acetone. And then we've got our feed temperature. We got our estimate for the exit air temperature. Then we can go about calculating. We have the feed concentration of acetone, the initial rate of reaction, given that concentration in our Arrhenius term. And then it's just that with a minus sign for the rate of consumption of acetone with respect to volume. And then we have our more lengthy expression to find the derivative of temperature with respect to volume and temperature of air with respect to volume. Then we have a calculation of the conversion. If we come back to the temperature with volume, it's a little hard to see, but you may notice that this takes advantage of a user-defined function that will compute the heat of reaction for us, given the temperature, okay? So that's how that works. Now, where it really starts to happen is when we come to the second cell, and so let me increase the zoom a little bit so we can see what's going on there. Okay, and now when we're computing the flow of acetone, we use the Euler method based on the previous value and the interval dV, which is the difference here between two of these, times the derivative of FA with respect to volume. That moves that along for us, and then we can get the ketene and methane by stoichiometry and the total flow, update that. The temperature, we integrate dT by dV using the Euler method. Same with the air. And then we move along, and these are the same calculations that we reviewed before, all right? So that is how we carry out the solution of the equations all the way down, all right? And then when we get to the end, we can take a look at what lies behind this with VBA. So let's do an Alt F11, go to the editor, and go to our simplified model and its module. What we have here are our equations for heat capacity. The only reason that we needed these, you might say, why do you need these? Because you were assuming constant heat capacity. Well, the reason we needed these was to compute the heat capacity at an intermediate temperature. And then also we use these to evaluate how much the heat capacity changed over a range of temperatures. And then we've got a function to compute the heat of reaction at any temperature, starting with a base heat of reaction at 25 degrees, and then computing for a given temperature what the enthalpies of our three components are, and then adjusting that, and we need a units multiplier here of 1,000 in order to get our heat of reaction. So this is the VBA that we have coupled into this solution. So let's go back over. And then we can take a look at the fact that if we come down the temperature of air to the end, that's supposed to be equal to 1250, and it's 1229.7. So what that means is that our estimate here for the air needs to be adjusted. This can be seen graphically by looking at a temperature plot where we've got the reactor temperature, and you can see the effect of the endothermic reaction here at the beginning, and then it's overtaken by the heat transfer from the air to bring it back up. But our air temperature where it enters here is supposed to be up here at 1250, and our guess here was 1100, so it looks like we need to move that up. Now we could do this manually, but another way to do it is just to invoke the solver and say we would like the T air error here, which is the difference between our actual air temperature at the bottom and our desired 1250. And we would like to drive this to a value of 0 by changing the T air 0, all right, value, which we guessed at 1100. So if we ask for a solve on that, let it work for a bit, and it thinks it's done. Looks like T air error is 0, so let's accept that. It's now got 1112.9, not 1100. It moved that temperature 12.9 kelvins, all right? And if we go to the bottom of the air temperature, we see that we're now precisely at 1250 where we would like to be. So we can come back now and look at that temperature plot, and we can see now it hits the money at 1250 and comes in at a little bit more than 1100 as we suspected. And there's a similar profile for the reaction mixture temperature. Having that in place, we can look at the plot of our molar flows of acetone and ketene, and we don't need to look at methane because it's the same as ketene, equimolar. And we can see that for this size of reactor, it looks as though the reaction has pretty much gone to completion. We have virtually no acetone left by the time we get to that. And so we can come back and look at conversion, and we can see that the conversion goes to 100% or 1. Okay? So coming back, this shows how we're able to take our simplified model and go through and set it up with an initial estimate and then use the solver to satisfy the 2-point boundary value problem of having that solved value for the temperature of air as it enters the end of the reactor equal to the specification. So let's go back over the slides and look at that. This was the spreadsheet. We've been through that. And then here we just show some of the key formulas in the cells, how we use the Euler method to integrate or solve for the flow of acetone. And then we use just the stoichiometry to get the ketene and methane. The concentration here is calculated exactly as the, whoops, let's come back around to that. Exactly as what we had a couple of slides back here. All right, this formula computes the concentration of acetone given the temperature, the flow, and the feed temperature, and the feed flow and feed concentration. So here we go back to this. And then the rate is given by our kinetic expression, and the differential of that is just the negative of that because it's disappearance. And then we use the Euler method for temperature, and we use the Euler method for the temperature of air. And the derivatives for each of these match very closely the expressions on our information flow diagram, all right, and what we derived for the equations in the slides previous to that. Okay, so that's how we get that, then this corresponds to the VBA code that we used. All right, and we already reviewed that. And then this is where we started, and we did not meet the specification. So we went to the solver and asked it to change that estimate for the air exit temperature at volume equals 0 to drive our error to 0. And then it was driven to 0, and we get our solution with our matching temperature profile and our molar flow rates and conversion profile. Okay? So that's how we go about solving that. And then what we're going to do here is we're going to move on and say, how do we go about solving the full model? All right? So let's come back for a moment. I'm going to come back a few slides. That's the simplified model, and this was the full model. So let's leave that there and come over to Excel, and let's close this particular. Not going to save it. I'm just going to close it because I can always solve it again. And now I'm going to load a file which is called Acetone PFR full model, or full model starter, whichever you have. And this is set up in a very similar way, but because we're using the full model now, it's more extensive. It does have the reactor specifications are the same, the heat transfer, the feed conditions, the acetone feed and concentration, etc., and the air mass feed of the air, and so forth. And here I'm starting with that 1100 estimate again, and I have an error which will need to drive to 0. But as we move to the right over here, we have some more information. This is what we had before, but now we have heats of formation of our 3 components and not the heat capacities that we had before, because we're not presuming constant heat capacity here. So we'll come back over and let's zoom up a little bit as we did before to see things a little bit more easily. Just a minute. I've off my freeze panes here. Okay, move things up. And as I come across from the left, it looks quite similar in terms of the initialization row. And again, this guy should actually not be 0. It should be copied up 1. Let me correct that. You should see that in yours. And then we now are dealing with enthalpies. So we compute the enthalpy here, all right, based on the feed temperature using the formula. The feed temperature we happen to know, and that gives us an initial value for the enthalpy. And the temperature is just the feed temperature. The enthalpy of the air we get in a similar way, and the temperature of the air is known. Then we can come across and get our feed air concentration and our initial kinetics, just as with the simplified model, all right? Rate of reaction, and there's the change of acetone flow with respect to volume. But then, instead of differential equations for temperature, we have differential equations for enthalpy, and these are just the UA delta T terms because we are accounting for enthalpy for the chemical reaction as we determine the temperature from the enthalpy given the flow rates of our various components. So we have these two, and then we come back over and we move down here, and here we have the Euler method again, stoichiometry, total flow, and for the enthalpy we use the Euler method now, and the Euler method for the enthalpy of air. And now when we want to know the temperature, let me come back to here, when we want to know the temperature, we now know the enthalpy, so we need to solve this nonlinear relationship, which has 3 terms in it, for the temperature to make sure that the right-hand side equals the left-hand side. So as we come and look at that, and we see that if we look at the formula here, it is now using excuse me, it's now using a VBA user-defined function to find the temperature. So it takes a little bit for this to update once I hit enter. And it's the same thing when we get over to the temperature of the air, is it uses a VBA routine to do that. So to complete the story here, what we have to do is we have to take a look at those VBA routines. So let's go over to Visual Basic. And we have the one that's called find T. And that has arguments of the current value of the enthalpy, temperature of the feed, and the current flow rates of our 3 components, all right, that we get from the material balance. Now, what the technique that's used here is one that you've seen before, and that is the modified secant method, where what we want to do is take this function of h, all right, and what the function of h is, popping back, is this equation here with all terms moved to one side of the equal sign, because we want to drive that result to 0. And so what we do is we start with a temperature, and then we perturb that temperature just a little bit, 1/100th of a degree, and then we calculate what is an approximation to the Newton's method, and that's the modified secant method. And then we continue this loop until it converges. And when it converges, then that's the temperature. Now, in order to do that, we have this FH, which is what computes that equation error for us, and this essentially calculates what we saw back here with all of these terms over on the left side of the equal sign. There's the minus sign that puts them, and then we get FH, and we'll have the correct temperature when this is equal to 0, And that's what this routine will do for us up here. And then we have the exact same thing down here for air. It's a little simpler, where we have the initial air temperature, the slight perturbation, the modified Newton's method, the secant method, and then we have to know how to get the expression for that needs to be driven to zero. And again, coming back, that's this expression here with everything moved to the left side of the equal sign. So that's how the VBA code works. So we come back, and we're back to the beginning. So let us home and zoom to 100%. And can't quite see it here, but over here you can see that our current error is 24 with our estimate of 1100. So it's the same type of situation that we've got where we need to adjust the air outlet temperature until the air entry temperature equals 1250. If we take a look at it right now with our chart on temperature, we see that we're not at 1250, all right? And as a result, we haven't satisfied that requirement starting at 1100, just like for the simplified model. But now this is more complicated calculation for the solver, because for all of the rows of this particular model solution, it has to use the VBA code and do the solution of the find T and the find T air all the way down in order to get the solution every time it modifies this initial estimate. So let's be patient and let's go to the solver. Same setup as before, and ask it to solve. And wait for a while. And it says that it's done. The T error is 0. And the estimate is now 1115.7. Now that is a little bit different than the estimate that we got for the simplified model, I believe. But the full model is a different model, and it's more comprehensive. So if we come back and look at our temperature plot now, you can see it jump down, and it's ending up at 1250 with a slightly higher air guess here for its exit temperature. And we have a similar curve for the reactor. Our molar flows look similar. Values are slightly different, and the conversion looks somewhat similar. It doesn't quite achieve 100% conversion at the same point down the reactor. Okay? So this is our implementation of the full model, all right? And you can see that it follows actually a very similar format to what we did back in the previous Bootcamp 3, where we were solving sets of equations that were a lot simpler. It's more complicated, but it follows the same format. And what it is it's really based on having a well-organized information flow diagram, so you know exactly how to set things up. So that brings me back to emphasizing to you that creating information flow diagrams can be very, very useful to you. So let us pop through that. This was the simplified model that we looked at and the curves for that, and I'm just doing this quickly. And then this is the full model with the initial error with the estimate at 1100. And these are the elements of that, and it shows here how we're using find T to get the temperature, all right, based on a given value of the enthalpy. And setting up the solver here and having it solve, and it gives the error to 0 and gives us the correct estimate. And then we have our adjusted and correct temperature profiles. We have our conversion profile and our molar flow rates profiles. Okay? So that about does it, all right? And then if we go, we've documented here what the code is for the find T and the find and the FH for that, and then the find T air and the FHA for that, which is what you're driving to zero. And then additionally, we made use of functions that compute the average heat capacity, and that is used in our calculations to determine the temperature. So we have these functions set up based on the NIST correlations. Okay, so that brings us to the end of our Bootcamp 4, where we've delved into the detailed modeling of a packed bed reactor, the ammonia reactor, and a plug flow reactor, the acetone cracking reactor. And these have been significantly different in certain ways. The first one was high pressure, and the second one was not, but it had our problem with the heat exchange we had to deal with. The first reactor we modeled was adiabatic, so that made the tracking of the enthalpy pretty simple from the feed enthalpy. But the second, we had to be careful there because we had heat transfer across the surfaces. So that takes us through to that. You have all the files associated with the examples that we used here and the examples from the previous boot camps. You also have PDFs of all the PowerPoint slides, and you're watching it, so you have access to the screencasts that go through this. So it's my hope that this has been useful to you. I will mention that I am always available to you to provide assistance or advice, or you can provide me feedback on the screencasts and the package, and I'd be happy to use that in subsequent revisions. And that brings us to the end of the boot camps for Excel and VBA. And I hope you've found these useful. Bye now.